All right, subscribers, welcome back to another episode of Science with Surback. Today, what we're going to be doing or talking about is getting a little bit further into detail about nuclear chemistry. So, just as a reminder, we talked or introduced nuclear chemistry and we wrote those nuclear equations. And now, what we're going to do is we're going to talk about nuclear transmutations and nuclear half-life. Okay? So before we get going into these notes, there's a few objectives that I have for you to be able to accomplish by the end of these notes. So objective number 1, use the half-life of a substance to predict the amount of radioisotope present after a given period of time. Objective number 2, calculate the half-life, age of an object, or the remaining amount of a radioisotope having been given any of the two of these pieces of information. And objective 3, explain how radioisotopes can be used in dating objects and as radio tracers. So just as a reminder here, remember the words highlighted in yellow and written in red are the ones you need to copy down as long or as well as the information I write as well. So we start with transmutations, and transmutation is another nuclear reaction that happens where you smash one particle into another. So in our example here, we're taking an alpha particle, which again is just the nucleus of a helium atom, and it's colliding with the nitrogen nucleus. Now, as a result, what happens is it produces this isotope of oxygen along with a hydrogen nucleus. Okay, so basically, bottom line up front, what's happening here is you're smushing two things together and you are getting a product. So again, think of a car wreck here where you're smashing those particular cars together, and then the end result is what you get on that right hand side. So you may be wondering, all right, well, we talked yesterday about how nuclei become unstable and they get that neutron to proton ratio that's out of whack, and we talked about the belt of stability and things of that nature. Well, how do particles smash into each other? Because there's a lot of empty space and they have to hit each other pretty hard and pretty correctly to make this happen. So what happens is this isn't a normal process. This isn't just an everyday process that we run into. We have to have a little help from these accelerometers. So a nuclear transmutation has to overcome those electrostatic forces, which, remember, electrostatic, think plus or minus. Think like a magnet in this case. To do that, they have to be accelerated very, very quickly. So what happens is scientists over the last 40, 50 years have built these accelerometers. Again, you can see that these things are called atom smashers, cyclotrons, synchrotrons, and they're all used to accelerate particles and smash them into each other. And we, being close to Fermilab's just outside of Chicago there, they have essentially a track where they accelerate these particles at extremely high speeds to allow for that transmutation to happen. So again, the only way we can get these things to smash together is get them going really, really fast. And we're talking, again, alpha particles, which is the helium nucleus, smashing into other particles. And we do it through our particle accelerators. Now, you may be thinking, okay, besides real advanced physics research and nuclear chemistry research, why else would we have or utilize nuclear transmutations? And yes, the research application is a big chunk of it, but what also is very significant is things like cancer drugs. So to make specific drugs or chemicals used for cancer radiation therapy, they go through this nuclear transmutation process. And so cobalt-60 is often used as a way to have radiation therapy, and it's very specific how they produce it, and you can see that all the transmutations that it undergoes to become cobalt-60, become that radioactive isotope and allow for that radiation therapy to occur in cancer. So there are medical applications as well as those detailed research portions too. Okay, so we've seen a few nuclear transmutations. What we're going to do here is we are going to briefly discuss that and then be able to write one of these equations. Okay, so we get to the fact where we have trans uranium elements, okay? So trans means after, uranium is talking about the element uranium. With this, again, these are produced synthetically, okay? What that means is us as humans have to smash these guys together or smash these particles together to produce these radioactive or these transmutated elements. What happens, because we're smushing bigger particles into already large pieces, already large atoms, they're going to quickly decay. And it's for those reasons that we talked about in the first section on nuclear chemistry. They quickly decay because that neutron to proton ratio gets out of whack and they get really above the belt of stability, and also they have more than 83 protons in their nucleus. So these things, again, are a specific method that we have for nuclear transmutation, and they have some specific qualities here. Okay, so now, again, I just want to introduce how exactly you would see a nuclear transmutation. Again, I want you to be able to write this, but I'm not going to pass this. We probably won't see it again. Okay, so it says write the balanced nuclear equation for the process summarized as aluminum-27. We have that business in parentheses, we'll talk about here in a second. And then on the right-hand side, it has sodium-24. Okay, so a lot's going on. There's a lot of symbols that are thrown at you. And so where we start with a nuclear transmutation is with our starting element here. Okay, so we have our starting element, which is aluminum-27. So what we do here, again, all we're going to do is write aluminum-27 exactly how it's listed up here. Then for a transmutation to occur, we have this business here. And so I'm going to refer to my little cheat sheet down here. This first particle that is in parentheses is that bombarding particle. Okay, so what that means is that this is the particle on the right-hand side or on reactant side. Okay, so we're going to write it right next to that aluminum. And what we're going to do, it has an N for a neutron. Now, an N for a neutron is going to look like this. I'm going to write it down below here. Remember, a neutron does not change the number of protons, but it does change that mass number. So we're going to have 1 over N to represent that we have a bombarding neutron. And then what we're going to have is this. We are going to have this substance that's produced, sodium-24. I'm going to write it exactly how I see it on my problem. And then the emitted particle is that alpha particle, okay? So the alpha particle, remember, looks like this, and it has the same mass and number of protons as that helium nucleus, okay? We can always double check to make sure that this balances out. So the atomic mass on our left-hand side is 27 plus 1, which is 28. On our right-hand side, the atomic mass is 24 plus 4, 28. Hey, our mass checks out. Now, our number of protons is 13 plus 0 on our left-hand side, so 13, and 11 plus 2, which is 13. So by doing this correctly and writing the correct particles, we have correctly written a nuclear transmutation. So again, besides seeing this, I don't expect you to be able to do this and be expecting you to do this. I just want you to show that, one, we're abiding by that equal mass on our left and right hand side, and two, we are having that transmutation where essentially we smush one particle into the other and we have some byproducts as a result of that. All right, so now, again, it's great that we see that. We've really been introduced. What I'm interested in is, hey, can you write a nuclear equation like we've seen in that first and second section of our nuclear chemistry? All right, so now we get to this. Radioactive decay and half-life. And this is really the meat and potatoes of today. All right, so if you haven't been paying attention, now's the time to be paying attention. So half-life, by definition, is defined as the time required for half of any given quantity to react. Okay? So what happens here is this. Every single isotope has a unique half-life. And so let's clarify that. Carbon 12's half-life is going to be different than carbon 14's half-life. Again, same atom, same element, carbon, but they're going to have different half-lives. Now, half-lives here are affected by temperature, pressure, and chemical composition. We're going to get into a little bit of kinetics you see down here. And as a reminder, kinetics are affected by each of these things. The other thing to note here, I didn't have you write anything down, but natural radioisotopes tend to have longer half-lives than synthetic radioisotopes. Okay? So that means that if we manually make it, or we man-made some particular isotope, it's not going to have as long a half-life as we would find an isotope that is naturally occurring in the universe. So you can see what I mean by this in something that's synthetically versus something naturally produced in terms of our isotopes. All right, so let's go through an example where we can recognize some half-life here. Okay, so this problem says the half-life of cobalt-60, which we just got done talking about, is 5.3 years. We want to know how much of a 1.000 milligram sample of cobalt-60 is left after 15.9 years. Okay, so on a problem like this, I haven't introduced a formula, but the first question that we need to find out is how many half-lives have gone by. So what we're going to do here, we're going to take the total number of years, which was 15.9. So we're going to take 15.9 years, and we're going to divide it by our half-life, which is 5.3 years. Okay? Now, you can take a calculator. Some of you can probably already see this, how many half-lives here we're going to have. And so we're going to take 15.9 and we're going to divide it by 5.3. Well, that works out nicely. We get exactly 3. And what this means is that we have had 3 half-life. Now, we want to answer, okay, how much of this 1 milligram sample is remaining? So what I like to do in problems like this, I like to start out with my 1 milligram sample. And I like to say, okay, this is my first half-life. Again, by definition, a half-life means half of this original sample has decayed. So now we have 0.500 milligrams. All right, so that was one half-life out of 3. So we need to go through another half-life. So I'm going to label this as our second half-life. And so again, it's half of this 0.5 has decayed. So now we're down to 0.250 milligrams. We still haven't reached all our half-life, so we need to go through one more half-life, our third and final half-life that we have calculated. And so when we go through that third half-life, again, we are decreasing half of this value here, 0.25, okay? So now we're down to 0.125 milligrams, okay? Now, some of you may have a more mathematical background here and recognize that there are some formulas. And the reason we have formulas is most of the time we don't have these nice round half-lives that we can deal with. And again, this was of cobalt-60, that isotope that is left. All right, so again, we don't always get these nice round half-lives. So what we do, we abide by that first order kinetics business, and we get into some kinetics. So as a reminder here with our kinetics, first order, you have the rate equal to K, which is your rate constant, times your N. And your N is your number of nuclei. Okay, now most of the time we're going to use the nuclei as our amount of substance that we have. If we put this formula, and we've done this before, and we derive it into the integrated rate law, it's much, much more useful for us. And the reason that it's much more useful is because we can have initial and amount of substance at a particular time. So what this formula allows us to do is it allows us to look at any amount of quantity that has decayed. It doesn't have to just be a perfect half-life. Now, again, there are some things that we need to work to get to that point, but this is much more useful because of this. It has your initial amount and it has your amount remaining after a certain number of half-lives, and it doesn't have to be a perfectly used half-life. Okay, another thing that we can do, again, derived from kinetics, because our rate laws abide by first order kinetics, we can utilize this formula here. And that's the half-life is equal to 0.693, which is a direct correlation of that formula I just showed you, divided by K, that rate constant. So we're going to utilize those formulas. You may want to keep those sheets of paper handy as we go through these particular problems. Now, something that I want to mention before we go through our example problems is how they express radioactivity here. And we probably should have thrown this into the very beginnings of our information on nuclear chemistry. But we have two units, the Curie and the Becquerel. And these are units just to say, okay, well, how much radiation is coming out of that radioisotope? Again, sometimes you would see half-life expressed like that. They've moved away from both of these units because they are a little bit old school and they're not as commonly used. But anyways, all right, let's keep moving on here and actually do an example problem. Of half-life. And again, I would say if you haven't really been paying attention, this is the part of today's notes that is important and that should be paid attention to. All right, so it says we start out with 1 gram of strontium-90. After a certain time period, 0.953 grams will remain, specifically after 2 years. Okay? We want to know what is the half-life of strontium-90. So what we do in this problem here is this. We are giving an initial and final substance. Okay? So whenever you're given an initial and final substance, you are going to use that integrated rate law for first order kinetics, where it has your Nt over N naught equal to negative KT. Okay? So listing out these variables here. Nt is your amount of substance at a specific time. So after 2 years, it is going to be this 0.953. Again, Nt is, okay, after you've had some of this substance decay, how much is left? Okay, so 0.953 is left, and that is grams. Now, our N naught, or our N sub 0, as some people may say, is your initial amount. Well, your initial amount here is 1.00. So we put 1.00 grams. And then our K is our constant. Well, our K is going to be our question mark. We don't know that, all right? And our T is 2.0 years. Now, it's okay to use the unit that they give you. What I ask is pay attention to that unit, because we may use years, we may use seconds, we may use microseconds and things of that nature to go through this process. But now we got all the players in the game and we can solve for K. So what I'm going to do here is I'm going to put this natural log of 0.953 grams divided by 1.000 grams equals our negative K. We do not know K, times 2.00 years. All right, so what I'm going to do in my calculator is I'm just going to get rid of this natural log business first, and then we will worry about this business solving for K. So our natural log of 0.953 divided by 1.000, close that parenthesis, equals this number here. Now, I'm just going to use this as a placeholder because I'm going to keep this in my calculator, but I'm going to write this down, that we get negative 0.048, and obviously there'd be some extra business written there, but because I already have it in my calculator, I'm just going to leave it like that. And that's going to equal negative K times 2.00 years. All right. Now I want to get rid of this 2, and I want to get rid of this negative. So what I'm going to do is I'm going to divide both sides by negative 2.00 years. Okay. So each side is going to be divided by negative 2.00 years. Okay. Now, again, I left this on my calculator, and I would suggest you do the same. And all I'm going to do is divide by negative 2.00, and I'm going to press enter. I get a value here of, let's see if we can get rid of the glare, 0.02407, so on and so forth. I don't like to use decimals in this case when I'm talking about K, so I am going to use 3 significant digits because that's what my years are, and so I end up with 2.41 times 10 to the negative second inverse years. That is my K, and I still, unfortunately, have not answered the question number 1, okay? And again, that's inverse years. Years is on bottom. I need to know, what is the half-life of strontium-90? And oh boy, all right, so I just found K. Well, if you remember back in your notes, the half-life is equal to 0.693 divided by K, all right? So all I need to do is substitute K with the value of K that we've just found. So our half-life here for strontium-90 is going to be equal 0.693 divided by 2.41 times 10 to the negative second inverse years. And all I'm going to do is plug this into my calculator. So I'm going to get 0.693 divided by 2.41 times 10 to the negative second, and I press enter. And my half-life here, I'm going to take this out of scientific notation, is 28.8 years by the time I round. So again, the half-life, I'm going to write this right here, the half-life of strontium-90 in these calculations here are 28.8 years. Okay, so now what I've done here is this. I have done a few things. One, I found the half-life. A lot of work because it uses both the integrated rate law for first order kinetics, and then it also used this half-life formula that we've talked about. Gets a little easier here on problem 2. It says how much strontium-90 will remain after 5 years. So again, we turn to our integrated rate law for number 2 here. And so we go through natural log of NT over N naught is equal to negative K times T. Well, NT, again, is how much remains after a certain time. We do not know that. That is the question that we are trying to find. N sub naught is our initial substance. It's still the initial starting substance or amount that we have, which is 1.00 grams. Our K, we just spent some work to get to our K, and our K is 2.41 times 10 to the negative second inverse years. And then our T for half-life is 5.00 years, okay? Because that's how long the problem wants to look at. Now, all we need to do is plug these values back into our integrated rate law. So we're going to have natural log of N sub T. We don't know how much remains over 1.00 grams, okay? This is all equal to negative 2.41 times 10 to the negative second years, inverse years, excuse me, times 5.00 years. All right. So there's a couple ways that you can solve this algebraically. What I like to do is I like to consolidate this business here, and then I worry about getting rid of my natural log. Okay. So again, what I'm going to plug in my calculator is negative 2.41 times 10 to the negative second. multiply that by 5.00, and I get negative 0.1205. Okay, and again, I'm going to write this down and then explain it. Natural log of NT over 1.00 grams is equal to negative 0.1205. Now, what I am going to do is this. I don't like dealing with the natural log business, so if you check it out on your calculator, on the scientific calculator, it's really nice here. The inverse of natural log is this e to this x button. So what I'm going to do mathematically is I'm going to get rid of this e to the x, all right, on both sides. So what I need to plug into my calculator is this. I need to put e to the power of negative 0.1205. So that's what I'm going to do right now. I'm going to put inverse natural log, which is this e to the power button, negative 0.1205, and I'm going to press enter. Now, I'm running out of room. I don't want to squish this business in here, so I'm going to grab another sheet of paper and we can continue on with this process. All right. So again, hope my paper doesn't fall off the edge of the table. But I'm going to continue with this process. Again, I just put this inverse natural log and I got 0.8865. All right, by the time I run. So 0.8865 is equal to NT over 1.00 grams. Now, from here, this becomes really easy, all right? So all we need to do is we need to cross multiply. And this is really nice because we're just going to take that value that we got, 0.8865, and multiply it by 1.00, which, again, you don't need to put this in the calculator, but we'll do for grins and giggles. Now, I'm going to round this to 3 significant digits. Because that is what we utilize for our years. And so this would round to 0.886 grams. So our NT is 0.886 grams. And I want to put a note here. This is amount of strontium 90 that remains after 5 years. And again, this should make sense. This should make sense because one half-life was 28.8 years. So we haven't even got to a fifth of the half-life. And so this should make sense why we still have a large chunk of what remains in our particular calculation. All right, so again, this was the meat and potatoes of this section. We have just a little bit more information to talk about here with nuclear chemistry, and then we will be good to go. All right, so with this here, again, this is our meat and potatoes, and this is a big emphasis on what we are going to do with half-life. All right, so moving on here to, well, okay, that's great. We can calculate half-life. What's the so what? And this has actually a lot of biological and geological purposes that we can utilize this for, and that's radiometric dating. So basically, radiometric dating is comparing, hey, how much do isotopes of this day and age have compared to what this particular dead organism has? And again, we'll get into that with carbon-14 dating, but it's utilizing that half-life to predict how much radioisotope should be there compared to how much we have now, and we can judge that age. We can actually solve that T for time to determine that age of something like a fossil. All right. Okay, so let's go ahead. Let's go through radiocarbon dating and specifically talk about that. All right, so radiocarbon dating utilizes or compares carbon-14 to carbon-12. And this has to deal with organic compounds. And the reason for dealing with organic compounds is as us, as living creatures, as we go through respiration, we have some natural amount of carbon-14. There's a proportion that all living organisms have because they breathe the air in and out. What they do when they dig up some particular fossil is they take a sample, for example, like a bone, and they analyze, well, how much carbon-14 is actually left in that particular bone. Well, they compare that to how much should be there, and they're able to solve that T for time, and they are able to determine how old some formerly living creature is. And it's all based on the ratio of carbon-12 to carbon-14. Again, it deals with the atmosphere and those living organisms, but it does utilize that business of half-life, and it does use that specific half-life of certain isotopes. Now again, carbon-14 is really good at determining living organisms. However, there is a limit. We can't determine anything or the age greater than 50,000 years old using radiocarbon dating. And that's because there's too little carbon-14 left in that organism to be able to accurately compare it to what we need to be able to compare it to. So there are other options. There's obviously numerous radioisotopes out there. And so one example here, if we've reached that 50,000 year limit, is to utilize uranium-238. Now, uranium-238, very important here, has a lot longer half-life. I don't have it listed here, but has a much greater half-life of what we have here. Oh, there it is. Half-life of 4.5 times 10 to the 9th years. Pretty gigantic half-life, okay? Again, we can actually approximate the age of the Earth using our uranium-238 and going through that process there. And that's because it has a larger half-life. All right, so the big takeaways here from nuclear chemistry is this. One, it affects the nucleus of the atom. When we have something that is giving nuclear radiation off, it's emitting that energy in the forms of particles from that nucleus. The other thing that's really important is we need to be able to write those simple nuclear equations, okay? Not the stuff that we talked about today. That was just kind of an introduction. And then the third thing that's really important in nuclear chemistry is that half-life. Being able to determine or being able to calculate any of those particular variables from the integrated first-order half-life or first-order rate of reactions, or utilizing the half-life to solve for K or the specific half-life itself. Now, everything else here is just kind of some extras that are icing on the cake. Now, I hope you have enjoyed this episode. I hope you've taken something away from the nuclear chemistry lessons. Again, the reason we do this, the reason we emphasize this, is it specifies or it talks about what is happening to that nucleus of the atom. As always, I hope you have enjoyed this episode, and if you haven't done so already, make sure you subscribe.